Hi guys, I'm Animation, and today we are taking on Microsoft's Quantum Coding Challenge, question number A1. This question is rather trivial, but we're going to try it anyway. It says that we are given n qubits all in the zero state, and we are supposed to generate an equal superposition of all of the 2 to the power n basis vectors on these n qubits. So what's a basis vector? A basis vector is any state in which all of the qubits are either 0 or 1, and nothing in between. So a basis vector is any place where these qubits act as classical bits. So they've given us a couple of examples. For n is equal to 1, these qubits can be either 0 or 1. For n equals 2, they can be 0, 0, 0, 1, 1, 0, or 1, 1. And you can extend this for n equals 3, as in 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, so they have asked us to implement this in an operation which will take those n qubits as an input and will have no output. So the output will be the state in which we leave the qubits, and they have provided us the method signature over here. So let's dive in and start pulling this problem apart. Now when we see a problem like this, the first thing that we should try to do is to factor out these qubits and see how each of them are behaving. And we'll do this by building slowly from 1 qubit to 2 qubits to 3 qubits. So when it's just 1 qubit, it is an equal superposition. These basis states are an equal superposition of 0 and 1. And this superposition, equal parts, is called the plus state. Now if you don't already know that or are not familiar with the Hadamard gate and stuff, I do recommend that you watch this video on basic qubit stuff, operations on them, and quantum logic gates. Now when you move this up to 2 qubits, you see that this 0, 0, 0, 1, 1, 0, and 1, 1 can actually be factorized into 0 plus 1 times 0 plus 1. Now don't pay attention to these constants, because these constants are just to normalize the probabilities, and they will all work out eventually. So once you can break this down, this set of 4 qubits, into this multiplication of 0 plus 1 into 0 plus 1, you know that neither qubit depends on the other. Both are individually in the plus state, and they have got no correlation with each other. Now let's build this up to 3 qubit systems. These are all of the basis vectors in 3 qubits, and we can express that as 0 plus 1 into 0 plus 1 into 0 plus 1, and that is very simply plus plus plus, the 3 plus qubits multiplied together. So now let's move on to the code. So I've already started by writing some boilerplate stuff in these 2 files over here, and you don't need to worry about that. You can download it from my GitHub page to run your own code. But this will help us test out our program. So let's try a qubit array of size 5 and 100 test cases. And right now, since we have not written our code, it's producing all zeros. No state is being produced. It's just one state. So now we want to convert that into a superposition of all of these basis vectors. So let's start by writing our code. So what we plan to do is to convert each of those zeros into the plus state by using a Hadamard gate. So we want to iterate over every single element in this array. So it's up to length QS minus 1. And we want to apply the Hadamard gate on the element of QS. And that was the entire code of this program. We are done with our program. Now let's run this and see what we get. So let the size of the qubit array be 8. And again, let's try 100 test cases. And now you see that you're getting so many of these basis vectors. I guess that you're getting all of those basis vectors in almost equal probability. But now let's just go ahead and test this on Codeforces. And just as you'd expect, this program passes all of the test cases. So that's it. See you next time. Bye-bye.